Today we're discussing a really interesting problem. We're discussing the problem of counting various strings of length n. This is a really interesting problem because we're using techniques which we haven't used before, such as we're using the counting rules, we're using recursion, and also we're using a lot of cool tricks that we haven't used before. So I actually liked looking at this problem a lot. So let's go over some restrictions. The first restriction here is that n must be equal to 3. So this n must be 3, which means that a string must be the longest 3 characters long. The second restriction that we have is that we're dealing with characters A, B, and C. So characters A, B, and C. These are the valid characters that we can use for this problem. Another restriction that we have here is that A must be between 0 and n. So here I'm using interval notation. This signifies that we can include 0 and we can include n. 0 means that you use no A's. That means you have no A's in your string. And then n means that you have all A's in your string. So that's also a valid string. Another restriction is that we have B, which can be between 0 and 1. So it's on that interval. Then we have C, which can be between 0 and 2. So I'm including 0, of course, just like I included 0 here. And then also I include 2 as well. So these are the particular restrictions that we have in this problem. And I will go over this. I'll guide you in solving this really cool problem, and you guys will have a lot of fun. Before we get started, let's look at some truths, examples, and then methods. Truths. So what do I know is absolutely true in this situation? The first thing that I know is that the maximum number of possible A's is n. Max A is n. The second truth that I know is that the maximum number of B's is 1. The third truth that we know for sure is that the maximum number of C's that we have is 2. Another truth that we know is that order does matter because we're dealing with permutations here. For example, if we have the string A, B, this string is not equal to the string A, B, A. These two are just not equal. So the ordering of these characters, it does matter. Another truth that we know is that the true independent variables here are n, b, and c. So the independent variables are n, b, and c. This is a really important point because it may appear A is independent, but A really depends on n, b, and c. Specifically, A is equal to whatever we have for b and c. So you add b and c together, and then you subtract that value from n, and then whatever you have left over, that's what you have as A. And this is a really important point to stress because it led to much confusion in the online discussions. Let's look at method 1. In method 1, imagine having a bag of all possible characters and then selecting n of them. And then after you have selected n of those, you then count the number of selections that you have. Essentially, that's what method 1 is about. So let's jump into it. Method 1. So step 1 is to make a list of all possible characters. Once you have the list of all possible characters, you will have something that looks like this. Let's call this PC for possible characters. You'll have A, then you'll have B, then you have C and C. Now you may ask, why do you have this? Keep in mind that you can have a maximum of 3 possible A's. Therefore, you have A in your bag 3 times, A. Then you can have a maximum of 1 B. Therefore, your bag has 1 B. And then also you can have a maximum of 2 C's in your bag. So essentially this bag contains every single possible character that you can select. And essentially you must consider the maximum. Now, step 2 is to use permutations to select items. So we can have another variable, let's call this S for selections, and with our permutation function, we're looking at really partial permutation, and to make that distinction between partial and full, a full permutation is when you select all the items. So that means when you're making one selection, you're selecting something of length that equals what you have. But in this situation, we don't want that. We actually want to select only 3. Therefore, if we're looking at what we have in this situation, we'll put PC here, which represents the items that we have in our bag. And then here, we will use N is equal to 3. So we'll put a 3 here. And again, this means that we're selecting groups of 3 items. The next step is to get rid of duplicates. In this step, you can have unique possibilities. So let's call UP unique possibilities, and we'll say this is equal to set of S. What does this mean? So this means that you take S, which probably has many selections that are repeated, and this will get rid of those repeated selections. So that is the purpose of step 3. Step 4 is simply to take those remaining selections and then get the count. When you do that, you can have the count is equal to length of whatever the unique possibilities are. And then this will leave you with that answer. Now, there are a few things to take in consideration. One is that in doing this, because we're doing permutation, there's a cost to that. Time complexity, we're looking at factorial. And then space complexity, we're looking at something which is on the order of n. So that's something that we have to take in consideration. Space complexity is really not that bad, but the time complexity is something that we have to take in consideration. So that's method 1. Let's look at method 2. Method 2 uses the counting rules to make a formula by summing the number of ways of all possibilities. According to the counting rules, the number of ways is equal to the length of the string. In this situation, we have the length of the string as n factorial divided by the product of each character factorial. Now you guys may recall that we have sigma notation, and sigma notation represents summation. In this situation, we have pi notation, and this represents a product. That means we are multiplying the factorial of each character. So for instance, let's say that we have 2 A's. We're going to multiply by 2 factorial. And this is really the crux of this approach. So let's get into it. The first step, step 1 for method 2, is to identify the cases that we have. And we have 6 different cases. I'm going to denote each case by C1, C2, C3, and so forth. So let's say C1, we have that as all A's. So that would be something like AAA, right? And then we have C2. In C2, we'll have 2 A's and 1 B. In C3, put that right here, we'll have 2 A's and 1 C. And then I'm going to write more cases over this side. For C4, we'll have ABC. So 1A, 1B, and 1C. For case 5, we'll have 1A and 2 C's. And then for case 6, C6, we'll have no A's, 1B, and 2 C's. So this represents every possible solution. So really we have more solutions, but every solution will be fit into these various categories or various combinations. And here we can apply the counting rule to find the total number of items that will be within this combination. Let's take a look. So using the counting rule that we have here, we'll have for C1, we'll have 3 factorial, which is the length of the string, divided by, let's see how many A's we have. We have 1, 2, 3 different A's, so we'll divide by 3 factorial, and then we'll multiply. Again, we're looking at the product of each factorial, so we'll multiply by how many B's we have. I see no B's, so put by 0 B's, and then we have no C's, so we'll do multiply by 0 C factorial. So if you do this calculation, you will end up getting 1. Now, I'm not going to evaluate this completely, but what I will do is that for each one of these cases, I'm going to set it up for you, and then you guys can finish on your own. For the next case, we'll have 3 factorial divided by, so let's see how many A's we have. We have 1, 2 A's, so we'll do times 2 factorial. How many B's do we have? We have 1 B, so times 1 factorial. And then we have no C's, so we'll just put times 0 factorial. Repeat the process for step, or not step, but case 3. We have 3 factorial, which is, again, going to stay the same. We're going to multiply by 1, 2 different A's, so we'll do times 2 factorial, which represents the A term. And then we have no B's, so we'll do times 0 factorial. And we have 1 C, so we'll multiply by 1 factorial. And now we can repeat the process for the other terms that we have over here too. We will have, it's an equal sign here. Let's see, we have 3 factorial divided by 1 factorial for the A, because we have 1A, 1 factorial for the B, because we have 1B, and 1 factorial because we have 1C. Repeat the process for C5, which is case 5. This will give us the number of possibilities that fall within this case. We will have 1A, therefore we have 1 factorial. We have no B, so we're going to list it as 0 factorial. And then we have 2C, so we're going to write this as 0 factorial. Or not 0, but 2 factorial. Blunder there. Next, we have the last case. We're going to have no A, so we're going to put this as 0 factorial. We have 1B, which is going to give us 1 factorial. And then we have 2 C's, which will give us 2 factorial. Now, again, I'm not going to go into the actual evaluation. That's going to be for you to do. Let's continue to step 2. Step 2 is to take the result of each one of these cases. So this is going to be a number. This is a number. These are all numbers. When you evaluate that, you will get numbers for all of the cases. Step 2 is to then sum the counts for cases. Specifically, what does this mean? This means you will have something such as put total count is equal to C1 plus C2 plus C3 plus C4. Hopefully you guys can see this. Yes, you can. Plus C5, then plus C6. And then this will give you the result. So for step 2, you are then looking at the summation of all of the result that you got from step 1. And that's essentially what you do for method 2. So method 2 is pretty cool as far as complexity. It's going to be, spatial complexity is going to be 1, because really you just have a heuristic, which is just a formula. Once you find that formula, you can just plug in the n, and then you get your number. If method 1 and method 2 had a baby, this would be it. Method 3 automates method 2 by determining the unique cases, then using the counting rules to determine the total number of cases. One of the questions that you may have had from method 2 is, why do we have 6 cases? Why not 7? Why not 12? Why 6? Why that number? One of the beauties of method 3 is that it will automate the calculation of those cases for you. So you don't have to do that thinking, no trial and error. You just have that number right there for you. In order to do method 3, we have 2 different steps. The first step is to determine the unique cases. In order to do this, we have to imagine having a bag. This bag would have the maximum number of items for B and C characters. Now, if you recall, we did something similar for method 1, but this is different because we don't need to care about the A characters. We only need to care about the B and C's, because A is a dependent variable, and therefore we can remove that from our analysis. So our imaginary bag would look something like this. It would have 1B, because we can have a maximum of 1B, and then it would have 2 C's. Now, what we're going to do with this imaginary bag is that we're going to pull out a grouping of items. And the catch is that we can only pull out a certain number of items from the bag. We're going to start off by pulling out no items from the bag. So we'll pull out 0 items from the bag. And then we'll pull out 1 item from the bag. Next, we'll pull out 2. Next, we'll pull out 3. And when we do that, this approach will generate the number of cases that we would have. Let's take a look. So if this is our bag, and then we pull out no items, we would end up with this. It would be an empty set. Now, one of the beautiful things about this is that this is equivalent to case 1 from method 2, because if you have no B's and no C's, then by the way that this problem is defined, we have to then fill in the rest of those characters with A. So that is equivalent to having the A situation, or the all A situation, right? Then, if we look at the case in which we're only pulling out 1 item from the bag, and again, we're really focusing here on the combinations that we can pull out from this bag. If we're only pulling out a combination and the size of what we're pulling out is 1, then we're going to end up only being able to pull out a B and then being able to pull out a C. And by the way, I'm going to call this one up here case 1. Put a circle around this. If I do this, then this will generate cases 2 and cases 3. Now, it may not be obvious, but what happens is, do you recall in case 2, we have 1B and then the rest are A's? Keep in mind that the way how this problem is defined, we're filling in the remainder with A's. So this is equivalent to having 1B and then all A's, which is the same thing as case 2 from method 2. And then here, we have only 1 C. We're filling in the rest of the characters with A. Therefore, this is equivalent to having
case 3 from method 2. Let's take a look at pulling out another grouping from the bag. So now the size of the selection that we're pulling out is 2. So we can only pull out a group of 2. When we do that, the unique items that we can pull out would be, we can pull out a grouping of B and C, and then we can pull out another unique grouping of having all C's. When we do that, we will see that this is going to be equivalent to case 4 and case 5. Now again, it may not be obvious, but do recall from case 4, we had 1B, 1C, and then 1A. And then in case 5, we had 2 C's and then 1A, right? And one of the beautiful things about this is that you get to see that A is really, that the A character is really dependent, right? You don't really care about how many A's you have. Technically, you do care about it, but ultimately, you can determine how many A characters you have by only defining the number of B characters you have and the number of C characters that you have. Now let's go back to the bag, and this time we're going to pull out a size of 3 items. If we do that, really we only have one selection that we could do, and that would be essentially all the items in the bag, which would be BCC. Now this is equivalent to case 6, in which we have, that's the C6, in which we have no A's. So once we have all of this information, we can then find out the counts of possibilities which will be generated by each case. Let's take a look at step 2. So step 2 of method 3 is to calculate the number of ways. Now, if you recall from method 2, we had used this formula, which was number of ways for each case. So I'll say number of ways for case I is going to be equal to n factorial, which is the size of the string, divided by the product of each character factorial. Now do keep in mind, when I say each character, I'm really referring to the quantity of that character. Next, we have method 4. Method 4 uses recursion via a top-down approach in which we start with n is equal to 3, and then we decrement this to n is equal to 0. Method 4 has 3 different steps. The first step is to define the function. We're going to define a function called way count, and this will take the independent variables, which are n, b, and c. N represents the number of characters in the string to be selected. As we mentioned, n goes from 3 all the way to 0. And when n is 0, that indicates that we can no longer select any characters. B and C respectively represent the values of B and C that we can select. The next step in method 4 is to define the base cases. And we have 3. The first base case, if any character count is negative, then return 0. So if B is less than 0 or C is less than 0, then return 0. The reason we return 0 in this situation is because this represents an impossible solution, meaning that it's invalid to have B or C being negative. We can't have that as a solution, therefore we return 0. All right, the next base case we have If n is equal to 0, then we return 1. The reason why this is the case is because this represents having an empty string as a solution. So an empty string technically is a solution. It is a solution in which we can no longer choose any other characters. That technically is a solution in that particular case when n is equal to 0. The next base case that we have occurs when b is equal to 0 and c is equal to 0. In this case, this is that situation in which we have all a's. So if you recall in method 1 and also method 3, we have the situation, well, really method 2 and method 3, we have the situation in which we have nothing but a's. This occurs when we don't have any b's and we don't have any c's. And therefore, we return 1 because that signifies having the AAA as that solution, which is really similar to this particular base case above 2, in which we have the empty string as that particular solution. The next step in method 4 is to define the non-base cases. And we have 3. So let's let C, actually we'll call this count, not C. We already have a C. So let's let count represent the actual count that we are following. Using recursion, we have to simulate various possibilities. If you recall, in methods 2 and 3, we had case 1, case 2, and so forth. We want to keep that information alive. We want to represent that. And the way of representing this is to consider all the possible things that could occur. This is really similar to quantum mechanics, in which you have many different things that could occur and then they do occur. Same thing here. We have to consider the situation in which we select A, or if we select B, or if we select C. So we're going to do some superposition, and we're going to represent that by adding all of those solutions together. So we'll do count is equal to weight count, and if we select an A, then the length of the string will decrease, so we'll put in n minus 1. B and C will not change, so we keep that the same here. And I'll put select A. All right. The other possibility that we have, so I'll do plus minus to indicate that we're using the previous solution above, is that we could select a B. And in that case, if we select a B, the string length is still decreasing, so we'll put this as n minus 1. And because we select the B, then that quantity is also decreasing too, so we'll put that as B minus 1. And then C is the same, so I'm going to put this as select C, or actually select B. There you go. Next possibility that we have is that we can select C. So here, using recursion, we're going to represent that possibility. And if we select C, the string is still decreasing. So we're going to put this as n minus 1. B is staying the same. And then C is going to be decreased by 1. So we'll put this as C minus 1. And this is selecting C. All right, so here we have it. We have all of these possibilities represented, and if you were to sum all of these up, then you would have all of the count, and this would be the solution for method 4. So we just discussed all of these 4 different solutions. We discussed method 1, which solves this problem via permutations. We discussed method 2, which solves the problem via counting rules. We discussed method 3, which is a combination of method 1 and 2. And then we discussed method 4, which solves this problem via recursion. Thank you.